Hi everyone, I hope you can hear me and I hope I'm live. So let's start. And those who are watching first time, let me quickly introduce myself. I'm Sachin. I'm co-founder and instructor at GoClasses. I've finished my masters from ISC Bangalore, and after that I have worked at Amazon as an applied scientist. And then I have also got All India Rank 33. Before ISC I got All India Rank 33, by which I got the admission in ISC. Right? Okay. Now let's start. So if you are having any doubt or anything, you can always join our Telegram group. This is the link, and also you can find the link in the description. And if you want to join the test series, then you can join the test series using this link, and link will be in the description. If you want to join the full course, then also you can join the full course. The link is also in the description, or you can just visit goclasses.in, and then here you can find you can find a way to join the full course. Okay. Hello Akash. Good evening. So now let's start. And in this video, mainly we are going to discuss shortest path algorithms. Okay. So in this video, what we are going to discuss, let me just write here, shortest path algorithms. So questions related to shortest path algorithms, mainly we will be discussing in our GATE syllabus, whatever we have, which is Dijkstra or Dijkstra. We also have Bellman-Ford, and we also have DAG shortest path. And then once we finish all of this, then I will discuss the difference between prims versus Dijkstra or Dijkstra, whatever you want to call. Okay, so then I will discuss this also. So basically this is the topic of today's lecture, and obviously we will be doing questions in between. Okay, so here and there we will be doing questions in between. Questions means only PYQs. So this is a series for PYQ. So that's why we will be just doing the PYQs in between. Okay. So this is the theme of today's lecture. And in Dijkstra, I will talk about everything, which means intuition. Here I will talk about intuition. Here I will talk about negative cycles, negative edges, these things in Dijkstra. And whatever else I can teach you. So I will talk about all the things in all the algorithms. Okay. So now let's start. I hope everything is fine from my side. Audio and video, everything is fine, right? Now let's start. So first is intuition behind Dijkstra algorithm. Now since this series is mainly aimed for the revision. So this is basically, let me quickly remind you that this is revision, which means theory. Okay, theory revision plus PYQ series. So which means I will be having revising you the theory, and we will be solving the PYQs, and not just PYQ. We will be solving very complicated PYQs only, complicated or simple looking also, but those have some concepts, or instead of complicated, let me say conceptual PYQs. Okay, conceptual PYQs. Okay, now let's start. Now I'm assuming that you know what is Dijkstra and how does it behave. But if you do not know, then let me quickly recall you. Let's suppose there is a graph that you have. Okay, any graph, and then what Dijkstra does. Let's suppose this is the graph that you have. Any graph that you have. Then Dijkstra will start from a source vertex S. And then it says that I can finalize one of the vertex. Let's suppose this vertex it will finalize. Then in every iteration it just relax all the outgoing edges. It will relax all the outgoing edges from this, and it will finalize all the vertices based on the minimum distance from all the known distances. That's what we do in the Dijkstra, right? It's very easy algorithm, very simple algorithm. We will do the PYQ, and then it will be a revision for you. But for now, let's just understand what is the intuition behind the Dijkstra algorithm, right? Which means why it is working in the way it is working. Or should I first tell you that how it is working? Maybe let me take the PYQ question. Okay, just a second. Let me take this question. Let me first tell you that how it is working, and then we will move to that why it is working. The question where I will tell you that why it is working, the way it is working. Okay. So yeah. Let me paste it here. Yes, I hope this is visible to everyone. Okay. Now let's just solve this question, and then it will just recall you that how Dijkstra works. Suppose this is the graph that you have, and in this graph what they are asking, suppose we run Dijkstra on this single source shortest path graph, and then they are saying in what order the vertices are going to get finalized. So let's just move this graph on the next page, and then let's just see that in what order the vertices are going to be finalized. So if you apply the Dijkstra algorithm, and this question has been asked in GATE 2004. So this is a question of GATE 2004. So like the source vertex should be given, and they are saying that P is a source vertex. Okay, if P is a source vertex, and let me also put the options in front of me, if we can eliminate the option after doing some some iterations. Let's just check. Okay, so P is a source vertex, so obviously initially it is 0 and everything else is infinity, right? I hope everyone can recall it. Initially it is 0 and everyone else is infinity. And then what you need to do, you need to just go through this this edge. I mean, initially this P is final, so if it is final, I am just shading it. Okay, either you shade it or you just double circle it or whatever you want. Okay, let me just shade it, and let me just say that that this is a initial vertex that you have. Now once you relax all the outgoing edges, this infinity will be 1, this infinity will be 6 because 0 plus 6 is 6, this infinity will be 7. Now what you need to do, you need to take the minimum out of all of this. What is the minimum out of all of this? I think 1 is minimum. So that's why you will be taking this one, which means after P you are choosing Q, and then if Q is final, I am just shading it. So if it is final, I will not touch it again. Okay, since it is final, that's why I will not touch it again. Now let's just relax all the outgoing edges. This is 1 plus 1 2, this will be 2, this is 1 and then this is 4, 1 plus 4 5, but earlier it is 6, so it will be 5, and I think there are only 2 outgoing edges, right? So now again pick the minimum among all the known distances, 7 5 2 and infinity. Which is minimum? I think 2, this is minimum, right? So just pick it. It means that you will be picking R. Now just relax all the outgoing edges, this and this. There are only 2 outgoing edges. This is 2 plus 1, this is 3, this is 2 plus 2, it is 4, right? Now it will get modified to 4. So now just pick the minimum among all. Can you tell me the minimum among 7, 3 and 4? I think 3 is minimum. You will pick this U. So now just relax all the outgoing edges from U. Since there is no outgoing edge, let's not worry about it. Now just pick the next vertex, which is minimum. I think this S is minimum. You will be picking this S, and then this is S. This is 4 plus 2 6, but it is already final, so you will not touch it. And also if you do it, then there is no benefit, but you will be not doing it. And then this is 4 plus 3, it is already 7, so let's not worry about it. If you want, you can update it. If you don't want, you can directly say that you can directly come from this, or maybe you can come from this. Both are the same thing, right? So so let's say that after S you are picking T. So PQRUST, PQRUST. I think B is the correct answer, right? So yes, B is the correct answer. It is an easy question, but it is there to make you revise that how Dijkstra is working. So how it is working, basically you pick the minimum and relax all outgoing edges. You pick minimum and finalize it. Okay, finalize it, which means you are not going to again pick this particular vertex. I hope you understood that what do I mean by finalizing. You are not going to pick this vertex again, right? This is the first step. I mean, there are only 2 steps. This is the first step, and the second step, what you do, relax all the outgoing edges. Relax all outgoing edges from picked vertex. These are only 2 steps that you have in Dijkstra, and what you do, you just keep on looping on these 2 steps, which means like there will be a loop. I will show you the code also, but for now I'm just telling you the pseudo code. There will be a loop, and you just keep on looping in this. There will be loop through it, loop till you pick all vertices. That's all. This is the pseudo code of Dijkstra algorithm, right? Very easy code, and very easily you can write the code also. It is a pseudo code. So I will tell you about the code, but you should be now understanding that what we are doing, right? We are picking the minimum, we are relaxing all the outgoing edges. That's all. Now we are picking the next minimum, we are relaxing all the outgoing edges. Now we are picking the next minimum. What do you think? How many times we are picking the minimum? I think we are running it V times, right? So we are running it V times. So I think we are picking the minimum V times, and we are basically relaxing all the outgoing edges every time. So this, yeah, I agree. I mean, you can write it V into these 2. Let's suppose these 2 are going to take some time. Let's suppose these 2 are going to take some alpha time, right? Let me just simplify it in very naive way. So this, since it is running V times, then V into alpha will be the time complexity, right? This is the time complexity. But finding this alpha in this way, it is not very convenient. So instead of this way, we will be just simplifying it another way. Okay, so finding this way is not very convenient. I will tell you that how to do it simply, and then we will talk about the time complexity later. Okay, so for now, I hope the pseudo code is clear to everyone. Now let's just don't worry about the time complexity and all of this. Let's just recall that what it is doing. You are picking the minimum, relaxing all the outgoing edges. So what you did in the first step, you picked this P, you relax all the outgoing edges, and then you said what? Then you said that this, if you want to go from P to any vertex, see what you did is very important, and that is where the intuition will be coming in the picture. So let's just understand that why it is working in this way. Okay, let's just understand that why it is working. I can tell you that most of the aspirants, maybe if I'm not wrong, then maybe 99.99% aspirants will fail to answer this simple question that why the Dijkstra is working in the way it is working. I mean, they can solve the questions, that's not a big deal, but they will not be able to answer why it is working. Like suppose they went to some interview, then they will be not able to crack this interview. Because if they ask you that why it is working, then most of the aspirants get failed. Anyway, let's come to the question. So what we are doing basically, initially it is 0 and everything else was infinity, right? Do you remember this? So let me do one thing. Let me, for just the sake of drawing it, let me just remove all the vertices which are not neighbor of this. Just for 1 minute I'm doing it. I will connect all the vertices back, but just for 1 minute I'm just drawing the graph partially. Okay, I'm just drawing a partial graph. I will draw the complete graph in just a minute. Don't worry, I will draw the complete graph in just a minute. For now, let's just have this partial graph. Okay, so anyway, initially everything is infinity. Everything was infinity. Then you relax all the outgoing edges from P. That's what you did, right? I hope you remember. See, initially in this graph, initially it is 0 and everything was infinity. Then you relax all the outgoing edges from P. This is what you did. Let's just do it. Okay, let's just relax all the outgoing edges from P. Then what will happen? This will be 0, sorry, this will be 1, this will be 6, and this will be 7. And yeah, that's all. I mean, these are the neighbors of P, and remaining entries will be just infinity for now, right? In this iteration, remaining entry will be just infinity. Okay, now let's just understand that what I'm doing next. I'm picking the minimum, which means I'm saying that P was finalized. I'm saying that Q is also final. That's very, very crucial. How I'm guaranteeing? Let's just answer this question. How I'm able to give guarantee that P to Q shortest is 1, right? How I'm able to give this guarantee? If I can answer this question, which means this is just a first iteration. If I can answer this question now, then maybe I can answer this question for the later iterations also. So let's just see that why it is working. Why saying this one and then I'm saying that this is final? Why not I need to explore it more? Why not I'm saying that what if you come from S later? I mean, there is new path that you discover. I mean, later what you will be doing? You will be relaxing probably some other vertices, maybe S, T, something like, right? So see, initially you just know that this is 1, this is 6, this is 7, and then later you will be relaxing this. I mean, you will be doing something, and then maybe let's suppose from this S there is some path to Q that is lesser than 1, right? That is probably possible, right? So what I'm saying is that how I'm able to give guarantee that this is the final. I mean, I cannot change it. Can anyone answer this? Can anyone answer this? How I'm able to guarantee that this is final and I cannot change it? And like, which means that why I am saying that if you even explore in future from S, if you even explore from future in S, then you cannot reduce this 1 to something. That's why I am guaranteeing, right? Or even T, like even if you come from S to T, from T to this Q in future also, then you cannot reduce this 1 to something else. There is a reason why I'm able to give such guarantee. Let me tell you that reason. Suppose, let's just say, okay, for the sake of example only, let's just say these are ABC. Okay, so let's suppose that these are ABC, this is S. Okay, I'm just renaming it just for the sake of example, and let's suppose this is C. Now tell me, if you if you relax it, then basically what you're saying, looking at only this graph, I mean the graph is huge, okay. I just drawn all the neighbors of S. I have drawn all neighbors of S. Graph is actually huge, okay. Graph may be huge. So from this moment only, it is saying that if you want to go to A, you can reach in 1. If you want to go to B, you can reach in 6. If you want to go to C, you can reach in 7. This is what we are arguing, right? Everyone agree with this? This is what we are arguing. Now we are saying that see, you can reach to A, B and C in just 1, 6 and 7. That's okay. Now we are saying, let's just argue one more thing. Can we give a guarantee that S to B is 6 final? Can we say S to B equal to 6 is final? I mean, you cannot reduce from 6. Can we give this guarantee? Tell me. Maybe not. Reason being is that what if in future you explore some path and then let's suppose this is a path of length just 2. Then you will say that see, instead of going S to B directly, why not you go to S to A and then A to this B, like that, right? You're agreeing with me? So suppose that in future you discover that okay, there is some path of length 2 only and this is already 1, then you in future you can say it is just 3, right? Just a second. Okay. I hope you are getting my point, right? So basically, can you guarantee that S to B 6 is final? The answer is no. The answer is no. Reason being is that maybe in future you discover from A that there is something 2. Okay, great. Now tell me, can you guarantee, if you can guarantee from S to B, then can you guarantee from S to probably C? Can you guarantee that S to C equal to 7 is final? S to C equal to 7 is final. Can you guarantee? Obviously no. Reason being is that maybe in future you come from A to C or maybe from B to C. Let's suppose this is 2, this is 3, something like that, right? So okay, this is, let's suppose 1 or maybe 0.5 or something like this. Let's suppose this is 0.5. Suppose that this is 0.5. Then in future you may find a new path, which is, I mean, when you discover this ABC, see, currently I have not discovered this ABC, I have just discovered this S. So in future you may come to know that from S to A and then from A to C it is just, you know, there is 1, it is 3, then maybe in 4 you can find out, maybe in future you can find S to B and then B to C is 0.5 or something. This is 6, then maybe in 6.5 you can reach, right? So basically you cannot guarantee to C also, right? I mean, you cannot guarantee to B because in future, what if you discover a new path? Similarly, you cannot guarantee to C. What if you discover a new path, right? If you see, currently we have not explored this A, B and C. We have just explored this S. But in future, if we explore, then we can find some shorter path, right? But okay, let me just show you. But can you guarantee? Let me ask you. Can you, you cannot guarantee to B, you cannot guarantee to C, can you guarantee to A? Let me ask this interesting question. Can you guarantee to A? Can you say that S to A equal to 1 is final? Can you say this? S to A equal to 1 is final? The answer is yes. Answer is yes. Reason being is that in future, even if you explore this B, even if you explore the C, it is saying that if you go via B, okay, whatever you do, if you go via B or if you go via C, whatever you do, then at least you are carrying 6 weight here and 7 weight here, which means 6 plus something will be there only. It cannot be lesser than 1. 7 plus something will be there only. It cannot be lesser than 1. So that is why I cannot guarantee to A, I cannot guarantee to B, I cannot guarantee to B, I cannot guarantee to C, but I can guarantee to A only. Everyone understood this? So that's the intuition behind Dijkstra algorithm. So here the assumption is that these edge weights are non-negative. These are only positive or non-negative, okay? Which means Dijkstra doesn't work for negative because in future I am assuming that you are going to carry the positive weight only. What if you carry negative weight? Then my algorithm will fail. In fact, my algorithm is not designed for the negative edges. That I will talk about it in just a while. But for now, we are understanding the intuition. I hope now you are able to recall the intuition that we are having, right? So that's how we built the intuition for the further iterations also that we did in the complete course. But anyway, like for the revision, I hope you got the idea that why Dijkstra is working. So basically it is a greedy algorithm, and it says that okay, whatever is the minimum, let's just pick it, because in future I will at least carry 6, I will at least carry 7 from here, right? So that's why Dijkstra is working. The first part is clear to everyone that why Dijkstra is working. Let me know. Akash, is this clear to you? Ratul, is this clear to you? Okay. Now this is how a Dijkstra code looks like, which means as I just said, like there is just a loop, right? In Dijkstra code, it is just a loop where you pick the minimum, relax all outgoing edges. That's how it looks like. So code wise, it looks like this. I mean, what you will do, there's just a loop where you pick the minimum and then relax all the outgoing edges from that. That's all. Now, what will the time complexity of this? Let's just talk about it. Okay. Let's just quickly revise this. That what should be the time complexity of this Dijkstra algorithm? See, what you are doing, you are basically having an array, and sorry, this is not an array. I mean, depends on the implementation, but it is better to have a heap. Like we can have a various discussion. I think we do have that slide here. Yes, so it could be a heap, it could be an array, it could be a Fibonacci heap, sorted array, unsorted array, linked list, whatever you want to take. So there is a data structure which is key of V, and then this key you can implement this using a heap, using a array or whatever, right? So what you do, you have all the initially you have this is 0 and all the initially distances are infinity, and then you pick the minimum. Initially you will pick this as a minimum, then you relax all the outgoing edges. So what you do here is that this, see, suppose you pick this minimum, then if you pick this minimum, if you relax all of these outgoing edges, then since this is just an outgoing edge, for how many vertices this is an outgoing edge? From how many vertices this edge could be an outgoing edge? From how many vertices? Obviously one, right? Or obviously only one vertices. This edge could be outgoing edge. I think only one, right? Only one. So which means you will pick this minimum and then you will relax all the outgoing edges. Now tell me how many times you are going to relax this edge. Since you are going to pick this minimum only once, that's why you are going to relax this edge only once, isn't it? Isn't it? Since you are going to pick this vertices only once, because just I pick the minimum and I never look back. This is what greedy says basically. You finalize something, you never look back. Let's hope for the best. That's what greedy says, right? So you will pick this vertex and then you never look back. You will say that okay, let me relax all these outgoing edges. So what you are doing, you are picking minimum how many times? You pick minimum V times, because you are picking every vertices, and with respect to edges you are relaxing edge. So relax edge how many times? E times. Basically you are relaxing every edge exactly once, right? So we are picking every vertex exactly once. Similarly, we are relaxing every edge exactly once, right? So like this is how you can simplify the simplify the analysis. Anyway, like we did it in the complete course, a very thorough analysis we already did. If you do remember, that's okay. If you do not remember, that's also perfectly fine. Okay, so here these are the two operations that we did. So which means it will be just V into pick min or delete min, like since we delete from the array or whatever you use, right? Array, heap, or whatever you want to use, we delete min or pick min because we never look back. So that's why let's say delete min, and then E into relax edge. So relax is just a decrease key or some distance updation. So this is relax. Now it will depend. Like if it is an array, then updating some value will take how much time. If you want to update some index, let's suppose this was earlier 5, and then you know the index, which is db, you know. Suppose you want to index that to 3. It will just take a constant time. In array, the relax is just going to take constant time. But let's not worry about the data structure for now. Like let's just write the thing in very general formula. So E into what should I say, relax edge or update key, whatever you want to say. Okay, maybe update key, because relaxing edge is just updating some value. Update key. Okay, if that is an array, probably unsorted array, I can say. If there is an unsorted array, then update key will just take order of 1, I think, right? If it is an unsorted array, and if it is a heap, then if you update some key, it might go to top or down depending on the min heap or max heap. Then it might take log of b, because in heap or in array, like the number of elements is v, right? Because I store all the elements, and initially for first vertex it is 0, and every other vertex it is infinity. So number of elements are v only. So that's why it is log v in case of heap. It is just order of 1 in case of sorted array, unsorted array, like that, right? But anyway, this is the general formula that we have, that you delete every vertex exactly once, you relax every edge exactly once, right? I hope everyone understood this. So that's how the Dijkstra is working. And then you can have this adjacency list and adjacency matrix formula. So in adjacency matrix, you will be having extra v square. This is what we have just seen, but in adjacency matrix you will be having extra v square, because you need to iterate through the whole matrix extra. This is just an extra job, and we understood this already, right? So basically, this is the complete chart that you can make based on this remove me and update key operation. Like if it is heap, if it is unsorted array, sorted array, Fibonacci heap, like that, right? So this is just a small revision for Dijkstra algorithm. Okay. Now I hope everyone understood the Dijkstra algorithm, which means everyone understood the intuition behind it. Working example. Basically we did one PYQ, and then I told the time complexity also. Okay, so these 3 things are done. Now let's move to the next question. In case of Dijkstra, that does it even work on the negative edges? Does the Dijkstra work on the negative edges? Let's just see this. Suppose you have some graph, you have this graph, maybe this graph that you have. Okay, this is 2, this is 5. Let's suppose this is negative edge, and there is no negative cycle, only negative edge. Okay, in fact there is no cycle. This is minus 10. Suppose this is S, or maybe this is A, this is B, this is C. Suppose this is the graph that you have. If you apply Dijkstra, it will say, okay, Dijkstra will say, if you can just apply it, very easy to apply, it will say that A to C shortest is 2. According to Dijkstra, it is 2, but in reality it is minus 5. In reality, A to C shortest is minus 5, isn't it? So tell me, Dijkstra working on the negative edge? Answer is no, right? Because in reality answer is different, and Dijkstra is giving you different answer. Now let's just see why it is not working. Reason being is that if you remember the intuition behind Dijkstra, what I said, let's suppose there are 3 vertices that I had. It was A, it was B, it was C, it was I think 1, it was 6, and it was 7. I said that I can finalize from S to A definitely, because in future, even if, just notice this point, in future even if I come from B, then I cannot reduce this 6, right? Which means that I cannot have lesser than 6 in future, even if I come from this B, and in future if I come from this C, I cannot have lesser than 7. But what if in future I discover that, okay, this is minus 10, then boom, everything is wrong, right? And that's violate our assumption basically. So in future I cannot carry the negative weight. That's what our assumption is, because there are no negative edges. But that's what it is happening here. Like I said that if you want to go from like initially I will say that this is infinity, this is infinity, and then initially I will say this is 5 and this is 2, and then I will finalize, Dijkstra will finalize this C, because in future if you come from this B, then I will be carrying something greater than 5. Basically, it cannot be lesser than 5. But it is minus 10, which is obviously not acceptable. I mean, if it is negative edge, then Dijkstra have not even assumed that negative edges can be present. It is not a fault of Dijkstra. Okay, it is not a fault of Dijkstra. It is not like a fault of Dijkstra. Dijkstra initially assumed, okay, or maybe let me just say he initially assumed that there could not be negative edges. Now you might say that, sir, if I have something like this, maybe let's say there is very simple example. Let's suppose if you have something like this, then in this case Dijkstra is giving you correct answer. Dijkstra will say that this is -1, this is 2, or sorry, this is 1. Dijkstra will give the correct answer, right, in this case. So it is not because the Dijkstra can work on this example or something like that. Basically, if it is working, Dijkstra is working on the negative edge, then it is just that you are so lucky. Okay, so if Dijkstra works on negative edge, then it is just out of luck. Dijkstra बना ही नहीं है negative edge के लिए. Okay, so Dijkstra is not even made for the negative edge. If Dijkstra is working on the negative edge, it is just because of luck. That's all. Okay. Rakesh is asking, is it necessary to find different methods of each PYQ in the gate? Obviously no. If you can solve with the one method in the gate, then in the exam hall, okay, in the exam hall, if you can just solve with the one method, it is obviously best. Why we will try another method? But here, while you are practicing, if you know different methods, then only in the exam the probability that you will be correcting that question is very much high. Otherwise, like, you may get stuck in the question in the exam because your concepts are not clear if you are not able to solve here with some different approaches. I mean, I'm not saying that every question could be possible with different approach, but if there is a possibility, then you should definitely try it. Okay, so you can read this paragraph later. Okay, I will keep this in the slide. Now I hope everything is fine. Now let's just move to the Bellman-Ford and let's just see that what is the intuition behind Bellman-Ford. Do you remember the Bellman-Ford algorithm? How does the Bellman-Ford work? So Bellman-Ford says that you run algorithm v minus 1 times and then plus one more time to detect negative cycle. Right, this is what the Bellman-Ford says. Now let's just understand that why in v minus 1 times it is able to give the correct answer. Suppose, okay, maybe let's have a question first. Okay, and using this question you should be able to understand this idea. So this is just a very easy true false question. What it says that consider the given graph and mark edges from shortest path from S to T, which means these edges are forming a shortest path from S to T. See, this if you go from this, if you go via this edge and maybe via this edge, like that. Okay, if you go via this edge and maybe via this edge, then this is the shortest path that you already have. This is given in this question. And if we relax all the edges in the order of S v1, which means first you relax this, and then you relax b1 to b3, and then you relax b1 to b4, and then you relax b4 to t, then we get the cost of the shortest path. That's what they're asking, true or false. Suppose this is initially 0. If you relax this, you will be getting 2, and I think 2 plus 2 you will be getting 4, 4 plus 1 you will be getting 5, and then 5 plus 2 you will be getting 7. Is the 7 shortest path? Obviously, I mean it is given to us. There is nothing extra that you need to do, right? So obviously it is a true statement, which means they have given you the shortest path. See, this will basically build the intuition for the Bellman-Ford. Okay, now you will get to understand that why Bellman-Ford is working. And again, I can guarantee you that like most of the aspirants, okay, maybe even 99, maybe even more than 99 or 99%, I don't know. Okay, most of the aspirants will not be able to answer that why Bellman-Ford is working in the way it is working. They just know that okay, just do this and get the answer. but that's not we do at Go classes, right? We just understand everything from scratch, that why it is happening the way it is happening. Okay. Now, suppose that you relax all the edges in this order, then you will get the correct answer, obviously, because this is the shortest path that we already have. Now, let me twist this question a little bit. Let me ask this question. So, this is true statement. Now, let me ask this question. This question is saying the same question, exact same question, just one extra line. Okay. This is saying that if you relax in this order and intermix with some more relaxation, which means that you will relax in this order only, which means you will relax x to v1 and then v1 to v3 and v3 to v4 and v4 to t, but in between you will be having some other relaxation. Maybe you can have, I don't care, maybe you can have s to v2 or any other relaxation, right? Or maybe it's the same relaxation, does not matter. Okay, so maybe s b4 to t, anything. Okay, in between let's suppose there are multiple relaxation v1 to v4 or anything. Okay, let's suppose in between there are multiple relaxations. Okay, so in between there could be multiple relaxation. What they're asking, even if you intermix this particular order. Okay, see, earlier they said like if you do follow this order, then you will get the shortest path cost. Now they are saying, can you intermix this with some other order and then still you are getting the shortest path cost? What do you think? What do you think? Like, even if you intermix with some other order, will you get the shortest path again? The answer is yes. Okay, very interesting. Answer is yes. This is true, and that's the intuition behind the Bellman-Ford. This is how the Bellman-Ford is derived, basically. Reason why it is yes, like why I'm saying that even if you intermix with the some other vertices, then also it is true. It is because let's suppose that I do have this graph, and then initially you do s to v2 or anything. Okay, before s to v1 you do anything else, maybe s to v2. So initially see everything is infinity, and then maybe I will use a different color. Okay, initially everything is infinity, and then suppose you relax this, maybe you relax s to b2, maybe you relax this, which means it will be 4, and then you can relax anything, maybe b3 to t or anything. Since it is infinity, it won't matter, but yeah, you relax anything else. Okay, and then you relax s to b1. Then the moment you relax s to b1, no one can stop it to b2, because this is 0, this is infinity, then it will be 2, right? And then you relax something, maybe in between you relax b4 to t or anything, b4 to t or anything. Let me just relax in any other edges. So instead of this edge, let me just relax maybe b1 to b4. So in between of this, let me relax b1 to b4. Okay, so b1 to b4, which means if I relax b1 to b4, it will be 6. And let's suppose I relax b4 to t, anything. Okay, whatever you want. Okay, let's suppose I relax b4 to t, whatever you want, and then this means this will be 8 or anything, and then I relax this b1 to b3, then this is 2 plus 2, this is 4, obviously it will be 4 only. See, earlier also, I mean earlier, even if it is not infinity, even if it is something else, since you know this is shortest, so it cannot be lesser than 4, because you know this is shortest, right? Because you know. Rakesh, please leave this session. Rakesh is saying any short trick and all. Rakesh, please leave this session. I humbly request you to please leave this session. This is not for you. We are not going to teach the short tricks and all. We are just going to have a thorough analysis. Okay. So you can do a self study, and please leave this session because it might not be useful for you. Okay. Okay, so let's just continue our analysis. So what we are saying that this is like what you have done, and this is now 4. Okay, now you relax anything, and then you relax b3 to b4. If you the moment you relax b3 to b4, see earlier it was 6. Now it must be. I mean, it cannot be lesser than 5, because this is 5 is shortest. 5 is shortest, so it must be greater than 5. Maybe 7, maybe 8 or something like this, right? Okay. Am I audible to everyone? I hope everything is fine. Okay, great. So let's just start. Now whatever you do, let's suppose after that you may relax any other thing. Maybe you try to relax this, then ultimately you relax this. This is 5 plus 2, which is now it will be 7 only, because earlier it was 8, but it has to be updated to 7 because 7 is shortest. So whatever you do in between does not matter to me, because I know here 4 is shortest. So whatever you do, maybe it was infinity, maybe it is 5, 10 or anything, but the moment you relax this, I mean you relax this and then you relax this, you will definitely get 4 here, you will definitely get 2 here, you will definitely get 5 here, you will definitely get 7 here. See, it was 6 and then from infinity it got 6 because of some intermix of relaxation, but then it it again got 5, right? So whatever you do, you will be always getting this as 2, this as 5, this as 7, this as 4, and then this is obviously 0 and this is also 4, because these are shortest. And whatever you do in between, it may just change this value to maybe something else, but since it is shortest, you will definitely be getting 5, right? Okay, so I hope everyone understood this. Okay. Now, if you have understood this, then you will say this is true, which means if this is the shortest path. Now let's just understand the intuition behind the Bellman-Ford. What I'm saying, let's suppose this some edge may be E5. Okay, let's suppose some edge may be E5 and then E2, then E3, and then let's suppose E1. Maybe let's suppose this is shortest path from edge to B. Okay, I mean you relax this, you relax this, you relax this in this order. This is the shortest path. Now in between you do anything, in between you relax anything, in between you relax anything, then you will say that you will always get shortest path even though you are relaxing in between anything. How it is making any intuition for the Bellman-Ford? Reason being is that, so let's now understand that why the Bellman-Ford is working in the way it is working. So basically it is called path relaxation property. If we relax in the order of shortest path, even though we intermix with some other relaxation, then also we will get the shortest path. Okay. So Rakesh, please do not spam here. Okay. Otherwise we will block you. Please do not spam. Now let's just go to this example and let's just try to understand that what is happening with the Bellman-Ford. So suppose that these are some costs that I have, maybe. Okay. So I hope you understood this property, that what we are doing, you are having a shortest path order, and then in between you do anything, you are not going to change the shortest path cost. Okay. Now let's just understand the idea behind Bellman-Ford. What it says that you relax B minus 1 times and you will get shortest path. This is what this algorithm says. You relax B minus 1 times and you will get the shortest path. So why it is saying? Because let's suppose you relax B minus 1. Let's suppose these are the edges that you have, maybe E1, E2, E3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10 or whatever edges. Okay. Let's suppose E1, E2, E3, E4 till E9 you have. Now suppose you relax these edges in how many times? 8 times. Which means, or maybe let me take a small example. Maybe let's just take E1, E2, E3, E4. Suppose you relax these edges, and there are, let's suppose, only 3 or 4 vertices, whatever. So you relax B minus 1 times. So first time you relax, then you can relax in any order, E2, E3, maybe E4, E1. Second time you can relax in any order, does not matter, E3, E4. Third time also you can relax in any order. Let's suppose you do in this order. Okay. Okay. So E1 and E4. Any order you can do, does not matter actually. So suppose you do this in this order. Now let's suppose there are only 4 vertices, 1, 2, 3, okay, 4 vertices only, suppose, and then there are 4 edges, maybe something like this. Okay, let's suppose this is E1, this is E2, this is E3, this is E4. Now if you want to find out the shortest path from here to every other node, then it will be either E1, E2, E3. I mean, it will be consisting only 3 edges, or maybe E4, E3, E2, or maybe just E4 or something like that. It cannot have more than 3 edges. Let's suppose from here you want to go probably till here only, okay, and then it is consisting these 3 edges, which is E1, E2, E3. Now tell me, do you have that order here? Do you have E1? I mean, are you relaxing in the shortest path order? You pick this E1 here, you pick this E2 from here, you pick this E3 from here. Which means you give me any shortest path, I will tell you that, see, you have relaxed in the shortest order. If you will say that E3, E4 and E1, this is my shortest order, then I will say that, okay, this is E3, this is E1, and this is E4 and this is E1. Which means that you will always be having shortest path order. right? And yes, it is getting intermixed with something, that's okay, which means you, for any path, there is a shortest path, and you can have the shortest path in this order. If you are relaxing v minus 1 times, you can have that shortest path. This is an intuition. I mean, let me just tell you in more concrete way why Bellman-Ford works, but there was some intuition, right? Or maybe because of lack of time, let me not go with this way. So we have already done this in the class. I hope you remember it. In the complete course we have already done it. So let me quickly recall you that that what we did. I mean, we have proved it in two ways, and very nice proof we have done. So let's suppose that let's just try to quickly prove it. Maybe we can have it soon. So suppose that there is a shortest path from S to BK, and this looks like this. So what I just did, I just told you a little bit of idea. I mean, if you have understood this idea, that's perfectly fine. I'm now going to tell you a more concrete idea that you should be able to understand. Okay. Suppose there is a shortest path that I already have. Okay. Which means this is not a graph. I mean, graph may be something like this. Okay. Graph could be any complicated, but I just told you the shortest path from S to BK, which is this. Now, my claim is that our algorithm will discover this path in not more than k steps. Why? Let's just see this. See, you will relax one time, and then you will relax all the edges two times, then you will relax all the edges three times. That's what you do. Suppose initially this is 0 and this is this. I mean, there will be some cost of these edges, but let's suppose this is 2, 1, 2 or anything, right? And these are infinities. I mean, the cost is infinity, and there is a weight of these edges. Okay, let me just have a different color here. This is 0, this is infinity, 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 right? Now let's just see what's going to happen. If you relax all the edges, maybe in any order, you relax all the edges how many times? K times. You relax all the edges k times in any order. Just do it. Maybe v2 to v3 in this order, and then vk minus 1 to vk. And there are, since in the graph there are many edges, okay? I mean, this could be the edge in the graph, which is v3 to k, vk. This is not the graph, this is just a shortest path, maybe v1 to vk minus 1, whatever, right? I mean, there are many edges in the graph. And then, since you're relaxing all the edges, you must be relaxing S to V1 also, obviously, right? And then you, let's suppose, relax anything, maybe V2 to V4, something like that, right? So you must be relaxing this, right? S to V1. The thing is that whatever you do, you must be relaxing S to V1. And since this is shortest, see, I now don't ask me why it is shortest. It is given that it is shortest, which means if you relax this will be 2 only. After you relax this will be 2. Which means that this will get updated to 2 only. Whatever you do, see, whatever you do does not matter, here, whatever you do, this will be 2 only. Ultimately, this will be 2 because it is shortest, right? It is shortest, it has to be 2. Maybe it got updated to something, let's not worry about it. Now, in the next iteration, you will relax all the edges. You will relax maybe v3 to v5, you will relax all the edges, but there will be a time when you will be relaxing this v1 to v2 also. I mean, you will relax all the edges, but you will be definitely relaxing this v1 to v2 because you are relaxing all the edges. Since you need to relax this v1 to v2 also, that means since this is 2, this is 1, this will get updated to 3. Now you will say that, okay, this will also get updated to, let's suppose this is 2 or something, this will also get updated to 4, but ultimately this will get updated to 3 because this is shortest and no one can defeat him. This is the best answer that I can have. No one can defeat him because I know this is shortest. So whatever you do, but here you will be doing v1 to v2, and after that whatever you do does not matter. You relax all the edges, even not just k times, you relax 10,000 times, okay? Whatever you do, no one can ever change this value to from 2 to anything and from 3 to anything. You relax any edge any times, does not matter. Once it is 2, it is 2. Once it is 3, it is 3. Reason being there, it is shortest, right? So that's how it is basically incrementally building the solution. I hope you understood the idea that how this Bellman-Ford is working, right? Okay, so this is very nice proof that we have done, and if you have any doubt, you can definitely comment it out. We will try to help you. Okay, we understand that if you are not from goclass's student, then you might be having some difficulty in understanding. Reason being is that you might not have studied things in the proof way. I mean, you might have studied, that's perfectly fine. But the chances are that you might not have studied in the proof manner. Okay. So these are the few points that I have written. I will share the slide with you, and you can find the slides in the description. So you can just later you can go on from this summary. Okay. Now, let's just solve this question. This is GATE 2009 question. It is saying that which of the following statement is correct about the Bellman-Ford shortest path algorithm? It always finds a negative cycle if one exists. May not be right. See, suppose there is a negative cycle. Suppose this is a graph, but there is a negative cycle that is not reachable. That is not reachable from your source vertex. Maybe let's suppose this is -3, this is 1, this is -10, and then sorry. Yeah, maybe yeah. So this is not a cycle currently, but I can make a cycle somehow which is not reachable from this. So let's just see. Let's just say that that the cycle is looking like this. Maybe let's have a cycle. Okay, let me go to the next page. Maybe let's suppose this is some node, this is some node, this is some node, and let's have a cycle which is not reachable. Not reachable. Maybe the cycle is this. Yeah, so this and sorry, these two should be in this way. Okay, great. Yeah, so I think this is a cycle. Let's suppose this is -10 to -30 or something. Okay, and this is the source vertex. Now what you do, initially everything is infinity. Okay, initially everything is infinity. You relax all the outgoing edges. I mean v-1 times. So you will relax this, you will relax this, whatever you do. Let's suppose this is 2, 3 and whatever, right? You will never update since you are never going to relax. I mean these are always infinity. You are never going to have this as something like this, and you are never going to update this infinity to something. These will get updated among themselves. You are never going to update these infinity. These will always be infinity. So can you tell me that there is a negative cycle after b-1 edges? Maybe you can say there are some nodes which are still infinity. At max you can say this. You don't know whether it is positive or negative cycle. You don't know. Maybe it is positive cycle. May not be even a cycle, right? So at max you can say that there are some nodes which are still infinity. Which means these nodes are unreachable. Can you say that there is a negative cycle? Can you be 100% sure? Obviously no, right? You cannot say. That's why you will say that a cycle always, or it can find the cycle always exists, then answer is 0, right? And find the cycle if it is reachable. Yes, if it is reachable, then obviously you will be finding the cycle, then you will be updating all the weights, and then you do it v-1 time, then you do it one more time, then you will get the answer, right? So answer is like P is not the answer, but yes, Q is the answer. Find whether there is a cycle which is reachable. So that's why Q is the answer. So that's why you will, I mean P is incorrect, Q is correct, that's why you will say B is the correct answer, right? Okay, great. Now let's just find the shortest path in DAG. See, suppose this is the directed acyclic graph that I have, and let me just redraw this graph. Okay, so I have just redrawn this graph. There is nothing else I have done. Let me remove these things. So this is just a redrawn of the same graph, which means that that I have not computed anything, I have not done any analysis. It is just a redrawn of the same graph. Okay, so let's just redraw this graph since it is a directed acyclic graph. So I should be able to redraw in this way. Now I want to find the shortest path from S to every other vertex. So what I will do, I will say, let's suppose I want to find from shortest path to A, from S to A. So I will say whatever number of paths that are leading from S to A, I will find all the paths, I will take the minimum among all. This is the one approach that I can definitely follow, right? I will find all the paths from S to A and I will take the minimum among all. This is what I will do. Now, this algorithm says that if you go from left to right, okay, which means if you relax all the outgoing edges from S and then all the outgoing edges from C and then all the outgoing edges from A, like that. I mean, if you relax all the outgoing edges from S and you relax all the outgoing edges from C, then haven't you discovered all the paths that are reaching to A? See, you can reach to A either from S or from C. So if you just relax all the outgoing edges from S, you relax all the outgoing edges from C, then you haven't you discovered all of these paths which are leading to A, then you take the minimum, right? And similarly, if you want to find the minimum from S to C, so you just relax all the outgoing edges from S, because there is no other path that can lead to C. There is only one edge. So if you relax this is just a shortest path. You relax all the outgoing edges from S, you relax all the outgoing edges from C, you will get and take the minimum, which means relax itself means minimum obviously. So you will get the shortest path from S to A like that. So if you go from left to right, which means in the topological order, if you go from topological order, then you can definitely find the shortest path. And how to get the topological order? If you remember the DFS, in the DFS there is a property that if there is a DAG, we have done this in the YouTube session also, that if there is a DAG, then the finish time of this, finish time of A, can anyone tell me the finish time of A and finish time of B, what is the relation? I will say you cannot finish this A, or yeah, you cannot finish this A before finishing this B, which means finish time of A will be greater than finish time of B. So for any edge this is true, for any edge in DAG, for any edge in DAG this is true, right? That's what we know. Now, which means that I can find the topological sort using DFS. So we can find the topological sort using DFS, which will just take order of B plus E, and then we can relax all the outgoing edges in this order, in the topological order. So basically find the topological order using DFS, which is going to take B plus E, and then this is the algorithm. Then you can just do this and it will just take order of B plus E. Okay, great. Now we have seen many things. I mean, we have seen Dijkstra, which says that pick the minimum and relax all the outgoing edges. We have seen DAG, which says that pick in the topological order and relax all the outgoing edges. We have seen Bellman-Ford, which says that relax edges in any order. It is very chill algorithm. Okay, it is very chill. It says that relax algorithm in any order, but it says that do it B-1 times. And then I'm making sure that if you do it B-1 times, then you will get the shortest path in shortest path for sure, right? So these two algorithms work for the negative edges, but this doesn't work for the negative. Dijkstra doesn't work for the negative edges, but yeah, DAG and Bellman-Ford can work for the negative edges, because there is no assumption that we have made for the negative edges in these two cases. Now let's come to the final thing, which is prims versus Dijkstra. Okay, so let me quickly tell you that what we do in prims and what we do in Dijkstra, and then we will just wrap it up. So what we do in prims is basically we start with one vertex. We say that okay, take the minimum of the cut. Basically we find the minimum of the cut, we find the minimum of the cut, and we say that okay, let me take this edge. Basically if we decide upon the edge based on the minimum. We start with one vertex, and then let's suppose these are all the vertices in the prims. I'm talking about the prims, right? So what you say that let's suppose these are all the edges from this vertex. You say that pick the minimum, and you start from one vertex. Then this is the first iteration, and in the next iteration what you do, you have one more edge. This is the second iteration. In the next iteration what you do, you have one more edge, which means this was the configuration that you have, and then you take the minimum among all, and then you pick one more vertex. Basically you pick one more vertex, you have one more vertex, not the edge. Edge is also okay, but vertex is more fine because you are bringing one more vertex. So this is what you do in the third iteration. That's what you do in the prims, right? And similarly you do in the Dijkstra. In the Dijkstra also you grow the tree in this way, which means you say that okay, in every iteration you finalize. In the Dijkstra we finalize a vertex in every iteration, isn't it? Which means earlier it is just one, which is source. Then we say that okay, let's take the minimum among all, right? Let's take the minimum among all. Then you finalize the next vertex, and then this is the second iteration, and which is the next minimum. Then you say okay, let me finalize the third minimum, whatever, right? This is the third minimum, this is the third iteration, like that. So basically both are essentially working in the same way, but there is just subtle difference, and the difference is very, very crucial. What is the difference is that, see, suppose that this is the min cut, which is let's suppose 2, 3, 4, and this is initially 0, and let's suppose in the prims, you are talking about the prims, you will finalize this vertex, right? And then once you finalize this vertex, let's suppose this is A, this is S, then you will say this is S to A I have, and then this is already 3, 4 you have, and then from A also there might be something, right? there might be something which is, let's suppose that okay, so instead of 3 4, let's have this as 5 5 6, like just for the sake of example. Okay, so this is 5 and 6. So what you did, you basically brought this a, and then you will say that okay, there are some other vertices that are leading that are outgoing from a. Maybe these are some edge costs. So let's have these edge costs something. Okay, so yeah, 2 plus like I want to have some edge cost which is basically, let's suppose, yeah, like just again, just for the sake of example, let's just have this is 10 and 15 so that I can have a clear cut example. Okay, this is, let's suppose, 10 and this is 15, this is 10, this is 15. Let's suppose that this is 2, this is 9. Okay, this is 9. Actually, I want Prims to pick something else and Dijkstra to pick something else. Just a second. So Prims will say that this is 10. So whatever is the minimum among all, Prims will pick this, right? Let's suppose that minimum is this. So Prims will pick this. This is 9, and this is 2. And then okay, let's not worry about the edge cost. So suppose that this is the example that I have, and then this is S, this is A. So Prims will take a minimum among all again, right? I mean, Prims has taken the minimum and Prims will take the minimum among all. Now this was the Prims. Okay, now let's talk about the Dijkstra. What Dijkstra does? Okay, and then you will be getting the difference. Dijkstra says that I will also take the minimum, but I will take the minimum based on S. See, this is 0, these are the S costs, so it is 2, 10, 15. So Dijkstra will finalize this A definitely, and then till now both are same. I mean, this was the 2, that is okay. Now Dijkstra will say I will count from 2. Maybe it is already 2, so I will say these are the vertices. I will again relax all the outgoing edges from A, and then I will say, let's suppose that that this is maybe 3. Okay, this is 2 plus 3, 5. Yeah, I want Prims to choose this and Dijkstra to choose this. So if Prims is choosing this, then this should be greater than 5, right? So which means, I mean, maybe this is 6. Actually no. Okay, so I'm not able to create the example, but I hope you are getting the thing. So what I mean to say, that what may so happen that Prims, see, in the first iteration everything is fine, but yeah, I do have the example in the next page. But what I mean to say, that Prims can choose, like in the first iteration everything is fine, but Prims will be choosing based on these just as cost. I mean, based on these as cost only. But Dijkstra will be choosing based on 2 plus these as cost, right? 2 plus these as cost. Let's suppose this is x, this is y. So Dijkstra will be choosing based on 2 plus x, 2 plus y, and let's suppose this is v. Let's suppose this is w1 and w2. So it will compare between w1, w2, 2 plus x, 2 plus y. But Prims will compare only w1, w2, and if this is x, this is y, then x and y only. Okay. So Prims may choose this, and Dijkstra may choose this. Dijkstra may choose something else. So basically, in the next iteration, things may be differing. Basically, if you look at the code, then these code exactly look same. The only difference is that in the Dijkstra you carry this. I mean, from the source you carry some weight, but in the Prims you do not carry this weight. Only this is the this distance. From the source you carry this distance. So only this is the difference. See, here you do not add this du, and here you add this du. So there is only one difference, which is this. In Dijkstra and Prims, and everything else is same. Right, we have done the complete analysis in the course, but I hope for the revision everything is fine for now, right? So Prims versus Dijkstra, main distinction is that it finds the closest vertex from the source, but Prims finds the closest vertex from this whole tree. It says that from this whole tree, what is the closest to me? And Dijkstra says that closest from the source. Okay. So prim's time complexity is exactly same as the Dijkstra time complexity, because everything is same, only this is the only difference. This summation is the only difference. So that is why both the time complexities are even same. Okay. So that is all for today. If you have any doubt, please let me know. And also, as a homework, what you can do, you can maybe you can produce an example here, just an example where very minimal example where Dijkstra and prims will be giving the different answer in the second iteration. Okay. Yeah. Thank you everyone. Thank you so much. Let's meet in the